So our next speaker is from Freescale Semiconductor. His name is Gaurav Gupta. He's a staff design engineer, speaking from India this afternoon. And the topic is bring IP verification closure to SoC, scalable methods to bridge the gap between IP and SoC verification. Gaurav is staff design engineer with the automotive group at Freescale and has worked in the area of functional formal verification and assertion IP development. He is involved in the verification of IPs and subsystems for advanced driver application systems consisting of image processing and serial interface IPs. Over to you.
Thanks, Mike. Good morning, everyone. I'm Gaurav Gupta. So I'll go through my presentation, and I think it would be a 20-25 minutes presentation followed by the questions. And the topic is bring IP verification closer to SoC, scalable methods to bridge the gap between IP and SoC verification. So essentially, the talk is about to be able to control the execution of a processor from the test bench, right? So let's look at the motivation that we had when we actually sort of came up with this methodology. So here I have tried to compare two different environments. One is SoC environment, and the other one is the IP environment. And so typically SoCs are synonyms with the CPUs. So there would be multiple processors, or at least a processor that would be part of the SoC. And typically the way execution happens at SoC is that there is a C code with bunch of instructions that we write, and we make a program, and that program is going to run on a processor. And it's actually the processor that controls the operation, be it data movement among various functional units, to memories, to IOs. So everything is done by processor, and test bench is merely a sort of just piece of code that actually triggers the processor and then waits for it to complete its execution. So there is no control of the test bench on the sort of data movement that is happening across your design. So there is no link between test bench and the processor. So that was something that that triggers the idea for this methodology to us, right? And then we thought that can test bench provide instruction that processor can execute, because through those C programs, what we are actually telling our processor is that these are a bunch of instructions, you go and execute it. So if those instructions can be provided by the test bench while we do SoC or system verification with processor, right? So that pretty much would solve the problem that we had. And contrastingly, if we look at the IP verification, it's the IP sequences and the sequencer. So typically we are actually using UVM, so I'd be using that methodology, but the idea that we have actually come up with can be used with other methodologies also. So typically in the IP verification flow, there would be a bunch of sequences running on sequencer, and then those would be driving some BFMs to the IP pins, right? And so the job of the processor is being done by the sequences and sequences at IP verification environment where processor is not involved, right? Now, so this particular execution flow for SoC or the designs with the processor has some drawbacks, right? Because we lose the controllability and flexibility that language like System Verilog and methodology like UVM provides to control the data movements across our design, right? And then because of that, typically SoC verification is limited to a few simple tests targeting some data paths, but to verify some parallel execution among different IPs and their interdependent interactions, it becomes a bit difficult, right? So idea was first to be able to reuse the IP level sequences that we already have developed as part of IP verification. Once that IP goes in and attached with a subsystem or SoC, and then that would actually eliminate duplicity of developing C patterns for that IP as well. So in case those sequences are reusable at SoC environment also, so that would actually eliminate the duplicity of developing C patterns for them as well. And then the last one was that once we have that kind of a test bench environment where even the processor is controlled through test bench, so it would be easier for us to control the data movements. So now let's look at the idea that we came up with to achieve what we have actually described as motivation. So we thought of so the idea is very simple. So what we thought of is to convert the atomic transaction that is triggered by a sequence into an instruction that CPU will understand and can execute on the fly during the runtime, right? So what we did was we thought of creating an adapter that would take one atomic transaction from the IP sequence and then convert it into an instruction for the CPU, right? So in a way, this particular adapter will provide a link for the hardware to software communication, right? And then CPU can actually execute that instruction, and typically it happens through a crossbar or peripheral through peripheral bridge to different peripherals, right? And if we actually decode that to the components at UVM level, there is always a UVM RAL transaction that would be initiated in order to access any IP right through its registers. So that adapter will go and convert that RAL transaction into an instruction and would write the details in the memory. So we used a few locations of the memory to create that kind of a protocol, right? And then CPU actually waits for that instruction to be available on certain memory locations, and once that instruction is available, it just fetches that and executes it, right? And then additionally, what we did was that we also dumped out some C files when we actually converted the atomic transaction into an instruction, and that instruction is dumped into a C file also. So it is just for the reference that these kind of transactions has been converted, and this is the equivalent C instructions for that. And another interesting point was that once we have this kind of an environment, so we still wanted to have the flexibility to run some traditional C program-based execution on that. And it could be because of the reason that you might have some legacy code that you want to run, or you might get some software from your software team that you would like to try out maybe some application scenarios or some use case scenarios. So with that environment, it is very easy to achieve because we can easily bypass this adapter and run that in traditional flow. And even what we were able to do was that the C instruction that we actually dumped out in the first flow that we proposed, we were able to make a program out of that, and then we were able to run that on the same environment that we created. So it's kind of a backward compatible also with the traditional flows. Okay. Now let's look at the kind of protocol that we defined to achieve hardware to software communication, and it's pretty simple. Idea is that any processor would need a transaction type, whether it's read or write, a transaction address, to which address you want to read or you want to write, and then the data that you would like to write, right? And then we created two flags. So one to indicate that there is a transaction that has come from the UVM or system Verilog side, and the other one is from CPU. So we call it SV flag and the C flag, right? And then we created one memory location to write the results also. So with these memory locations, we are able to create a protocol that would enable hardware-software communication, and basically the atomic transactions created from UVM RAL side now can be converted into an instruction, put down into the memory buffers that we call as porthole buffer. And then the CPU can actually fetch these instructions one by one, execute them, and then unblock the UVM side to get the next instruction. Okay. So now let's look at a simple case study. So this is a simpler view of the subsystem that we employed this methodology on. Right, so here there is a crossbar with bunch of masters, one memory as slave, and then a peripheral bridge connected to multiple peripherals, right? And these peripherals are shown as component 1, component 2, and then there is a memory that they interact to a RAM controller, right? And then there was a camera interface which was off platform for this particular subsystem. And and which is controlled via control module, right? So this is typically the architecture of any SoC or subsystem with processor that we would see. And then let's see how the execution in proposed flow would work, right? So in order to actually have a processing flow, what we needed to do was that we needed to generate a configurations for the peripherals like component 1, component 2, so that we were able to do by randomizing few sequences in the current flow. And then we started the image transfer from the camera interface. So again, it's off platform, so it could be started from the test bench itself. Processor has no role to control this particular off-platform peripheral. And then once there are enough lines in the buffer, we started to trigger these components to process that data. So again, it is being done through a sequence that was written, right? And then in the end, we are just kind of waiting for the relevant bit to be set to indicate that the entire data processing has completed. So this is again like apart from this camera interface, everything else is controlled by the processor. So what we did was here is that we are running sequences which are UVM sequences, and then converting those atomic transactions initiated by those sequences into an instruction, and that is still being executed by the processor. And in order to do the same thing in the traditional flow, we just have to sort of write equivalent C program for step 1, 3, and 4, right? So we could actually write C programs, just compile them, put the hex in the memory, and just like the traditional flow is being run. Right. So now let's look at some of the benefits and the applications that we were able to do with this kind of a flow. Right. So one of the application was generating a performance metric that we'll talk about in a little bit. But first of all, the benefit that we get out of this kind of approach is that we could reuse our IP label sequences, put them together to make a interdependent data path, right, where multiple IPs are involved, and create a sort of a sequence graph, right, by or just sort of create a processing steps for particular by combining all these sequences for independent IPs, right? So here stimulus creation is easy because now we just have to know that what each sequence does, right, irrespective of how that sequence is being controlled. Right, it might be something that has been done by the IP verification engineer, and the subsystem verification engineer may not know the nitty-gritties of these steps. But still, I can actually relate to that because I know if I need to transfer data from camera, I can just do that through a sequence, right? And then easy to control and visualize parallel threads, because now the flexibility that we get out of the languages like system verilog and UVM, we can make use of them to control the processor, because now processor is like a slave for our test bench, right? So it becomes easy to control that. And then because now the additional benefit that we get out of using system Verilog to create these instructions is that on the fly we can randomize it also, and it will support the seed-based randomization. So so we can actually create multiple configurations within the same test, right? And that will help to close the verification coverage, right? Because now for the interdependent interactions among IPs, we can create data paths with varying configuration in one test itself. And then the approach that I have shown here is scalable to multiple CPUs. So it's not that it is employable only to a processor, because each CPU would have equivalent adapter. So that would be the simplest form of employing this methodology on a design where multiple processors are involved. Or we could think of multiplexing it based on the design, right? But then it will depend. But the simplest would be that each, there would be a buffer for each of the CPU to operate upon. Okay, and now let's look at the application that we created out of that was to generate a performance matrix. So if you look at the component 1 and component 2, so role of these components is to process the data that is actually coming from the camera interface or through a camera, right? So these component actually works on different configurations, and in different configurations they would be accessing the memory in a different manner, right? So we could randomize the configurations of these components through IP sequences, and because we are able to randomize, we can actually dump out that statistics across configurations within our test, right? And then we are able to process that data in order to make a performance profile. So if you look at the graph that we have shown here, so the x-axis shows the number of access by a master, like how many cycles it takes to do an access on memory, any master. And then on y-axis it has been shown that what is the number of stalls that it actually encounters, right? So if you look at this graph, around 11 cycles there is no stall, but beyond that, if we do accesses, then the stalls are exponentially increasing. These kind of statistics, right, to complete the data, to generate these kind of applications profile. So just to conclude, so with this approach, we were able to do the stimulus portability. We were able to achieve reuse of IP sequences at SoC or subsystem level, and then we get the greater control in terms of randomization and threading that UVM and system Verilog provides. And then again, like the methods are scalable, as I told you earlier, and it opens a whole new dimension for test bench controlled system level verification, I would say, right? Because this is just one example that we have quoted, but because we now can actually randomize and control everything from the test bench, the opportunities would be immense. So that's it. If there are questions, I can take that. And just to note that we have shared few sample codes in the backup section, some flowchart of the protocol that we have defined, and some sample code that has been shared to implement this methodology.
I think we're going to go to questions now. So I've got a question. Gaurav, can you just back up a slide to your conclusions, please? Yeah. Oh, that's it. It says validation could also be a beneficiary. Can you explain what you mean by that, please?
Yes. So now we are dumping those instructions in terms of a C instruction as well through the adapter. So those instructions can easily be used to create a program that could be sort of used to do the SoC, traditional SoC verification, or even the validation, right? Because now you can use them to bring up your design quickly.
So, And one other question is, what's the performance of this? My experience would be potentially that it can take a long time to generate the hex, get it into memory, and then the CPU to execute that instruction. And then you also mentioned that the CPU sends back the results of that instruction. So is there a big overhead in this technique?
Yes, so let me try to explain that. So in terms of performance, so there is hardly a penalty because it's not a post-processing that we are doing. So what we do here is that on the fly during the runtime, as soon as there is a transaction through UVMRAL that would be converted into an instruction to CPU to execute. Now CPU will take that instruction and execute that just as it used to have been doing when hex was loaded in the memory, right? Because even then it has to do a read to fetch that instruction from memory and then executes it. So now also it will do the same, right? And then probably to expedite the process, what we can do is to write an ASM. So that's what we have done. So we have written an ASM code where we are actually using CPU registers directly to expedite that process of fetching that instruction from the memory buffer. And the other question was related to performance, right? So in terms of execution or the fetching of that instruction, there is hardly a penalty by employing that methodology. Yeah. So I think I forgot the other question. Okay. And one more thing to note here, when we actually show this application profile, right? Now, because this application profile is actually dependent upon component 1 and component 2 executing instruction that has been loaded, right? So it has no bearing on this M0 processor shown as master 0, fetching those instructions and putting that into the memory, which is shown as S0, because these components are triggered once that the entire hex code is available, or the instructions code is available in the S0 memory. So execution of component is dependent of execution of the main processor.
I've got a question. Has this enabled you to port directed tests written in C to target hardware for testing the ASIC when it comes back?
Gaurav, did you hear that question?
Not very clearly.
I'll repeat the question for you. Are you able, the tests which you generate pre-silicon and simulation for SoC, are you able to port those to the silicon when it returns to do silicon testing as well?
So the basic bring-up test that we created using this methodology were sort of ported to the silicon also, right? Which is okay. So under the hood, those are just few register accesses, right? And then we try to control some of the things from that. We try to configure the IPs and then tries to trigger that through processor. Once those IPs are triggers, everything remains as is in the system, right? It's the initial step where the choice is loading a precompiled hex into the memory and then processor fetching data from that memory and executing the instructions, versus providing those instructions from the RAL, doing the configuration, and then let processor control the data movement.
So I think that was a yes if you do
yes.
the preloaded C tests, yeah?